Have you ever wondered if there's a hidden pattern in the numbers that surround us? From the populations of cities to the prices of goods, from the lengths of rivers to the financial transactions we make every day, is there an underlying structure to these seemingly random digits? It turns out there is, and it's known as Benford's law. In 1938, physicist Frank Benford stumbled upon a surprising discovery while thumbing through the pages of a logarithm book. He noticed that the pages corresponding to numbers starting with 1 were much more worn than those starting with higher digits. Intrigued, he analyzed datasets from various fields and found a consistent pattern. In many real-world datasets, the leading digit is more likely to be small. Specifically, 1 appears as the first digit about 30% of the time, while 9 appears less than 5% of the time. This curious phenomenon became known as Benford's law, or the law of first digits. So, what exactly is Benford's law? In mathematical terms, it states that in many naturally occurring sets of numbers, the probability of the first digit being d is equal to log 10 1 plus 1d. This leads to a specific distribution of leading digits, as shown in this chart. We see that 1 occurs as the first digit about 30% of the time, 2 about 18%, and so on, with 9 appearing as the first digit less than 5% of the time. Now, you might be thinking, why would numbers behave this way? It turns out Benford's law applies to data sets that span several orders of magnitude and aren't artificially constrained. Think of data sets like populations of cities, lengths of rivers, or financial transactions. These data sets often result from combining other distributions and naturally span a wide range of values. Let's look at some real-world examples. Here we have the populations of US counties, the molecular weights of compounds, and the daily trading volumes of stocks. When we plot the frequency of their first digits, we see they all closely follow the distribution predicted by Benford's law. It's a remarkable fit. Now, you might be wondering, does Benford's law always hold true? The answer is no. While Benford's law has been found to apply to a surprisingly wide range of data, there are certain conditions where it breaks down. Datasets that are constrained to a narrow range of values like human heights or exam scores typically don't obey Benford's law. Similarly, datasets with built-in artificial constraints like prices set at psychological thresholds, $1.99, $9.99, etc., also violate the law. Mathematicians have studied the conditions under which datasets are expected to follow Benford's law. They've found that datasets that span orders of magnitude and result from combining other distributions tend to obey the law. In essence, Benford's law emerges naturally when we mix different distributions together. So, why is Benford's law important? Beyond just being a mathematical curiosity, Benford's law has practical applications in fields like data science and forensic accounting. One of the key uses of Benford's law is in detecting fraud and data manipulation. In financial records, tax returns, and election data, people who make up numbers often fail to follow the expected distribution of first digits. By comparing the actual frequency of leading digits to the distribution predicted by Benford's law, auditors and data analysts can quickly flag suspicious data sets for further investigation. For example, if a company's financial data has too many numbers starting with 5, 6, or 7, and too few starting with 1, it may indicate that someone has been cooking the books. Similarly, if election results from a particular region deviate significantly from Benford's law, it could suggest vote tampering or election fraud. Understanding Benford's law gives us a powerful tool to recognize when datasets may have been manipulated. It's a testament to the unexpected patterns that emerge in the numbers around us. Let's consider a hypothetical scenario. Imagine you're an auditor tasked with checking a company's financial records for potential fraud. How might you use Benford's law in your investigation? One approach would be to extract all the numbers from the financial statements and calculate the frequency of each leading digit. Then, you could compare this distribution to the one predicted by Benford's law. If there are significant deviations, especially in the higher digits, it could be a red flag that warrants further scrutiny. But here's a question to ponder. What legitimate reasons might cause a dataset to violate Benford's law? Perhaps the company deals in transactions that are consistently within a narrow range, like selling products that all cost between $50 and $100. Or maybe there are industry-specific pricing conventions that skew the distribution of leading digits. As an analyst, it's important to consider these possibilities and investigate further before jumping to conclusions about fraud. Now, let's consider another scenario. Suppose you're analyzing sales data from an electronics store, and you find that the leading digits of the sales amounts don't follow Benford's law. What might you suspect, and what would you investigate further? One possibility is that the store has been consistently rounding prices to attractive thresholds, like 99 or 199. This could skew the distribution of first digits away from Benford's law. Another possibility is that someone has been fabricating sales data and they didn't know to make the leading digits follow the expected distribution. To get to the bottom of this, you might look at the store's pricing policies, examine individual transactions for rounding patterns, and cross-reference sales data with inventory records. The key is to use Benford's law as a starting point for investigation, not a definitive proof of fraud. In conclusion, Benford's law is a fascinating phenomenon that reveals an unexpected regularity in the leading digits of many real-world datasets. From populations to financial transactions, datasets that span orders of magnitude and aren't artificially constrained tend to follow this law. Understanding Benford's law gives us a powerful tool for detecting fraud and data manipulation. When datasets deviate significantly from the expected distribution of leading digits, it can be a red flag that warrants further investigation. However, it's important to use Benford's law judiciously. Not all deviations indicate fraud. There can be legitimate reasons for datasets to violate the law. As data scientists and analysts, our job is to use Benford's law as a starting point for asking the right questions and digging deeper.